Let's start by talking about why we need to learn this exercise. Okay, so previously we have talked about that if we have a building on a slope, in order to convey water away from the building, we need to install a swell on the high side of the building like this. Now, what if the building is very long, like this one? If we maintain the building entrance from the high side here, you can either elevate the entire building with pillars or you can fill this entire area with fill, right? What if the building is even longer? Then your pillars needs to be higher or the amount of the fill will increase, right? So this approach could cause a lot of problems. For example, the construction could become too expensive when the pillars gets too tall or the amount of the fill becomes massive. The building will appear overly heavy as well in terms of its aesthetics. So instead of setting the FFE high and enter from the high side, what else could we do to correctly drain water away but keeping site disturbance at a minimal? Let's compare a few other scenarios here. Now, these scenarios apply to when the buildings are not wood-framed buildings. Okay? If they were wood-framed, then you'd have to use pillars because the walls cannot retain soil behind it. If you remember the retaining wall lecture for last exercise, the contours are stacked up vertically on the walls as shown here. So our first scenario to compare here is if we enter from the lowest end of the building with a low FFE. Now in this case, you can see that you have to cut all the soil in this area to build this solution. A potential disadvantage is that you may not be able to have any windows on the high side. What if you enter the slope with a medium FFE? Now you could have a relatively balanced cut and fill, right? And yes, you now have windows with fresh air and sunshine on the high side too. Now let's take a look at the contours in the plan view. Note that I rotated the plan from the last slide counterclockwise because this is the orientation you're more familiar with. The plan is not showing any contours inside the building, and we talked about this in the retaining wall lecture that contours will run on the walls in this case. So the plan on the right that has the contours in the building is not correct. Instead, they stack up along the outside wall, right? Again, they should not show up on the grading plan to avoid confusion. Here is a perspective showing how the contours on the sides of the building wrap up around the building walls, and then how the uphill swale works to direct water away. Now let's move forward to talking about how swales work with multiple structures. This space map here is very similar to what you will work on for exercise 9 as mentioned before. So you should be able to apply what you learned in this demo directly to your exercise. As you all know now, this is the drainage directions and swell contour pattern around a single building. So what do you do when you need to grade a group of buildings? Seems very complicated, right? But let's think about where you want water to flow first. First, of course, you'd like the ground around the buildings to slope away, creating positive drainage, right? And then next, just like grading for a single building, let's treat the three buildings as one big group. So you'd have a big swell on the high side of this group of buildings to run water across the site. And lastly, the areas in between buildings will enter into the big swale or flow downhill. Now let's revisit a topographic concept that we learned in our first lecture, a saddle. We talked about that a saddle has two summits with a low area in between, and in this low area, water drains from the two summits to the middle and then runs downhill in two directions, as shown by the purple arrows. And this point in the middle is called the saddle point. Now, if you replace these two summits with buildings, because buildings are essentially summits compared to their surroundings, and you compare this to the proposed water flows we just drew, then you can see that we're essentially trying to create two saddle points in between the buildings, here and here. Now, knowing that we need to create saddle points between the buildings, let's sketch out what the contour patterns needs to be to create the saddle points. Let's do it in a highly conceptual way for now. Okay? First, you all know now that we need a big swale that goes around the entire site that would look something like this. Next, the saddle contours need to look like this to run water away from the building corners. Now you may have noticed that we are in fact trying to create two smaller swales that runs in these two directions. So the two saddle points are actually HPSs. Okay? Now all this is very conceptual. This is just trying to help you envision the contour patterns around the buildings. Next, we'll do a demo of how to start looking for a grading solution. Where exactly do we start? Again, there's no single perfect way to proceed step by step. So as usual, what we provide here are simplified recommendations. So in the case of buildings becoming retaining walls, the FFEs are now less important than the ground elevations of the corners because, as we talked about in these previous slides, you can choose to enter the building from the top of the slope, the bottom of the slope, or from the side. So essentially you can choose any elevation between the highest and lowest corner elevations as your FFE. Okay? So the corners are where we start for this exercise because they determine the shaping of the ground, including the swales. So now let's set some trial elevations for the corners. How do we do that? We'll set them at roughly the natural grade of that location. And why is that? Because these trial elevations set roughly at natural grade will give you a start that tends to minimize the earthwork needed, right? Because we set the goal here to be maintaining the original grade for the corners. Again, try to estimate, no need to calculate. So for instance, it looks like this corner is in the middle of the 84 and 85 contours. So let's set that at 84.5. And this one, not exactly on the 81 contour, but close enough. Let's just set it as 81. Okay? Now, moving forward to other key elevations. The HPS for the saddles in between the buildings. Okay? In order to create positive drainage away from the buildings, we need to set the HPSs here lower than the corners, right? So again, we estimate. We can set the left one at 83.5 and the right one as 82.5, lower than any of the corner adjacent to it. Okay? Next, we need to examine how much space we have uphill to set a trial elevation for the HPS of the large swale. And it looks like we'd be able to fit in the 87 and 88 contours uphill. So the 86 contour will need to be the first contour forming the large swale. So we could set the HPS slightly above 86 as 86.1, and then we could try to sketch out the 86 contour like this. We don't know how to finish the 86 yet because we haven't set these two upper corners for the upper building yet. So we don't know where the contour will attach to the walls of the upper building. So next, we move forward to setting those two spots. They can be determined by calculating a 2% slope over this distance. So let's say they're roughly 86.2. Okay? Now we can complete the remaining portion of the 86 contour. Next, we'll move forward to sketching out the first contours that form the small swales. Okay? Conceptually, they should look like this, right? Conceptually, with the left one being an 83 contour and the right one being an 82 contour based on their HPS we set before. Let's start with the 83 contour on the left. We know this portion on the left needs to be V-shaped to form the large swale. Then this next portion forms the small swale on the left. Then we find out that, oh, this corner here of the building is 84.5, which is above 84, so there should be another small 84 contours here. Now we finish the 83 contour on the right for the big swale. Okay? Next, we move forward to the 82 contour that forms the small swale on the right. So similarly, this portion of the 82 contour forms the small swale here. Then this portion forms the big swale on the right. Now we move back to the left. This portion again forms the large swale, and the last part helps to form the swale, the smaller one, on the left. Now, in order to find out where exactly the contours hit the building walls, basically you'd interpolate between the two building corners. For instance, for the building on the right, the two corners are 83 and 81, so 82 should hit the wall right in the middle. Okay, so interpolate between the two corners based on the green line distances. Now let's continue with the 84 contour. This one is simpler. It mainly forms the large swale. A key thing to notice here is that it runs on the lower side of these two corner spots. Okay? Moving forward, we now work on the 85 contour that forms the swale on the left and hit the building corner that's right at 85.0 elevation. The right portion forms the large swale as well, but will hit the right wall a little higher than the lower right corner of 84.5. And lastly, we work on the 81 and 80 contour that complete the swales. Okay, now we've finished our first draft of contours. What we haven't identified yet are the FFEs. Remember that we said the FFE can be set at any elevation between the highest and lowest corner elevations? So in fact, that's exactly what we could do here. So for the upper building, your FFE can be set as any elevation between 85 and 86.2. For the left building, any elevation between 81.5 and 84.5. For the right building, any elevation between 81 and 83. So then what exactly should you choose? In the real world, many other factors can come into play. I'll give you one example. For instance, when people see the courtyard space between the buildings, they would naturally look for entrances facing the courtyard, right? So if that's the case, the building FFEs will be determined by the elevations of these three building sides. So for the upper building, its FFE should fall between 84.5 and 85. Okay, for the left building, its elevation FFE should fall between 81.5 and 84. And for the right building, it should be between 81 and 83, right? And if you like to place the doors exactly in the middle, then the door elevation and FFE will be the average of the two corners, right? So now we have completed our draft. It is time to critique it. Okay, the red contour lines here actually made it quite clear what are some of the areas of improvements. Okay, there are so many contours that have been moved far away from their original locations, which means there is a lot of earth moving here. We're causing a big site disturbance with this draft. So can we make it better? And how do we make it better? If we look at the uphill portion here, both 87 and 88 had been moved. How can we make them stay closer to where they were? So what about moving the HPS and the center line of the large swale closer to the building? That way, the 86 and 87 contours can stay closer to the building, and the 88 does not need to be moved. And then, when you look at the draft contours, you'll see that most of them are now on the uphill side of their original contours, right? That means we're cutting a lot. The newer elevations are lower than the original elevations. We're cutting a lot. So we need to overall bring the elevations up to reduce that cut. So to do that, how about if we elevate the HPSs for the small swells at the saddles? For example, from 83.5 to 84.2 on the left, and then from 82.5 to 83.2 on the right. Doing that, you'll be able to keep the proposed 84 contour much closer to its original location. Similarly, 83 will stay very close to the original 83. So those are the key changes made to reduce the cut. Now let's clean up the drawing and finish the rest of the contours. Adding 85 here. Then move to 82. adding 81. And you can see here you don't have to move the 80 contour anymore. Lastly, let's put these two drafts side by side, and you can see that the second draft is not that red anymore. There is much less contour movement here. So iteration is really key to any grading project. It can lead to a major improvement of the quality of the space and significantly reduce construction cost. Okay?